A faint streak crosses the night sky, unnoticed at first by human eyes. In mid-October 2017, a telescope perched on a Hawaiian volcano captures it, a dim speck racing through the void. Unlike the asteroids or comets that drift in orderly paths around the sun, this object moves with reckless speed, unbound by the star's gravity. It slices through the solar system, a traveler from beyond, caught only in its fleeting exit. Astronomers, alerted by the Pan-STARRS telescope, turn their instruments toward it, but time is short. Within weeks, it fades into darkness, leaving a trail of questions. Named Oumuamua, a Hawaiian term for a messenger arriving first from afar, this object defies the familiar. Most celestial bodies in our system orbit the sun, tethered by its pull. Planets, asteroids, comets all follow predictable arcs, but Oumuamua, hurtling at 26 kilometers per second, traces a hyperbolic path, a one-way journey through our cosmic neighborhood. Its trajectory, tilted against the plane of the planets, suggests it came from deep space, perhaps another star system 30 to 80 light-years away. The light we see from it began its journey centuries ago, a snapshot of a distant past. At first, scientists assume it's a comet, an icy wanderer warmed by the sun, shedding gas and dust in a glowing tail, but no tail appears. Telescopes, including the Hubble, scan for the telltale coma, a fuzzy halo of vaporized ice, but find only silence. Perhaps an asteroid. Then, a rocky fragment cast adrift, yet its surface gleams, more reflective than the dull stones orbiting nearby. The Spitzer Space Telescope, sensitive to infrared, stares for 30 hours, seeking heat from sublimating ice. It detects nothing. Oumuamua, a few hundred meters long, slips through categories, neither comet nor asteroid. Its shape deepens the enigma. As it tumbles, its brightness surges and dips every 8 hours. A lighthouse beam in the void. This pattern, captured by ground-based observatories, reveals an object elongated, perhaps 10 times longer than wide a cosmic needle, or a flattened disk spinning chaotically. Asteroids in our system, battered into potato-like clumps, rarely stretch so far. Comets, spherical when dormant, sprout tails near the sun. Oumuamua's form, unlike anything local, hints at an origin where different forces sculpted its frame. The object's speed, faster than any natural body we've tracked, suggests a long exile. Ejected from its home system perhaps by a stellar collision or planetary tug, it drifted for millions of years, battered by cosmic rays. Its surface, shiny yet scarred, bears the marks of this journey. Astronomers, racing to analyze data before it vanished, calculate its path. Entering from the direction of Lyra, near the star Vega, it swings past the sun, then exits toward Pegasus. But Vega, 25 light-years away, moved long ago. Oumuamua's origin blurs, a trail lost in the galaxy's churn. As it recedes, a stranger anomaly emerges. After rounding the sun, Oumuamua should slow, its energy sapped by gravity. Instead, it accelerates, a faint but measurable push defying Newton's laws. This non-gravitational force, detected in precise orbital tracks, baffles researchers. No visible gas jets, no dust trails explain it. The object, silent and sleek, moves as if propelled by an unseen hand. Scientists scramble, checking calculations, ruling out errors. The acceleration, though small, is real, a whisper of something new. Initial theories point to solar radiation pressure, the gentle nudge of sunlight photons. Solar sails, human-designed craft, use this force to glide through space. If Oumuamua were a thin, lightweight sheet, sunlight might push it, but its tumbling motion and lack of heat emission clash with this idea. A comet-like outgassing, where ice vaporizes into jets, seems plausible, yet the absence of a coma undermines it. The object's behavior reflective, elongated, accelerating resists every model, a puzzle carved from the stars. Astronomers, limited to weeks of observation, gather scraps of light. The Canada-France-Hawaii telescope maps its spectrum, seeking chemical clues, but finds little beyond a reddish hue, typical of irradiated surfaces. The Very Large Telescope in Chile tracks its motion, confirming its interstellar roots, By December 2017, Oumuamua is too faint, slipping beyond reach. Its brief visit, a mere glimpse, leaves humanity with data too sparse to decode its nature. Yet the questions it raises ripple outward, challenging the boundaries of what we believe possible. Oumuamua's fading light lingers in the data, a cipher from the cosmos. Its acceleration, defying gravity's pull, sparks fierce debate. Solar radiation pressure, the force of sunlight on a thin surface, seems a logical culprit. Engineers at NASA have long studied solar sails' gossamer sheets propelled by photons. If Oumuamua were such a structure, perhaps a natural flake of exotic material, sunlight could nudge it faster. But its chaotic spin, like a bottle tossed forward, suggests a denser body, not a fragile sail. Its reflectivity, brighter than local rocks, lacks the uniformity of a crafted surface. Another theory posits outgassing, like a comet's jets. When comets near the sun, their ices water, carbon dioxide sublimate, thrusting them off course. Oumuamua, passing within 1/4 the Earth-Sun distance, should have warmed enough to vent gas, yet no trace appears. The Spitzer Space Telescope, designed to catch faint emissions, sees no dust or gas. Ground-based scopes, like the Gemini Observatory, find no coma. If outgassing drives its speed, it's invisible, a ghost comet unlike any known. This absence forces scientists to rethink what materials could act so subtly. Daryl Seligman, a researcher at Cornell, proposes a radical idea: Oumuamua as a hydrogen iceberg. In the frigid depths of molecular clouds, where stars are born, hydrogen can freeze solid. Such a body, heated by the sun, might release pure hydrogen gas, undetectable by our instruments. This could explain the acceleration without a visible tail. But critics, including Harvard's Avi Loeb, counter that hydrogen ice is fragile, evaporating under starlight long before reaching us. Oumuamua, intact after eons, seems too robust for such a delicate form. Jennifer Bergner, at UC Berkeley, offers a simpler twist. Oumuamua could be water ice, bombarded by cosmic rays over millions of years. In lab experiments, such irradiation traps hydrogen gas in ice's lattice. Near a star, this ice restructures, releasing hydrogen in tiny bursts enough to push a small object without spraying dust. This dark comet, as Bergner calls it, mimics a rock but acts like a comet, its activity hidden. The theory fits known physics, using common materials, yet Oumuamua's shape and shine stretch its plausibility. Avi Loeb, a Harvard astrophysicist, challenges these natural models. Oumuamua's anomalies, its elongation, reflectivity, acceleration, don't align neatly with comets or asteroids. He suggests a bolder possibility: alien technology. A light sail, a millimeter-thick craft designed to ride starlight, could match Oumuamua's behavior. Its acceleration, driven by solar photons, needs no gas. Its shape, flat or needle-like, fits a constructed object. Loeb's calculations show a thin, reflective surface could survive interstellar travel, tumbling from a long-ago collision. The idea, published in peer-reviewed papers, ignites controversy. The scientific community splits. Some dismiss Loeb's hypothesis, citing Occam's razor-simpler explanations, like exotic ices, should come first. Others, intrigued, argue the universe's vastness makes alien artifacts plausible. Loeb, undeterred, launches the Galileo project, seeking physical evidence of extraterrestrial technology probes, satellites, relics. He critiques science's caution, urging openness to ideas that challenge dogma. Oumuamua, he argues, exposes our bias toward the familiar, a failure to imagine beyond Earth's templates. The object's shape, inferred from brightness swings, fuels this debate. If a disk, it might resemble a sail, its spin a relic of ancient forces. If a cigar-like rod, it could be a fragment of a larger structure. No telescope resolved its form, leaving room for speculation. Simulations at institutions like Caltech model its tumble, suggesting a violent ejection from its home system. A planetary disruption, where a star's gravity tears worlds apart, could launch such shards, their shapes forged in chaos. Oumuamua's surface, reddish from cosmic ray bombardment, offers few clues. Spectra from the Keck Observatory show a hue like Kuiper belt objects, irradiated over eons, yet its reflectivity, 10 times brighter than typical asteroids, hints at a smoother or icier composition. The lack of infrared glow puzzles researchers. Comets, warming near the sun, emit heat. Oumuamua's silence suggests a cold, inert body or something engineered to absorb little energy. Each datum, meticulously gathered, deepens the riddle. The acceleration, tracked by the European Southern Observatory, remains the crux. Its push, equivalent to a feather's nudge, grows stronger as Oumuamua recedes. This pattern matches solar radiation pressure, which weakens with distance, but not outgassing, which spikes near the sun. Loeb's sail fits this curve, yet natural theories persist. Nitrogen ice, like Pluto's surface, could sublimate invisibly, but its rarity in interstellar space strains credulity. Each hypothesis, tested against sparse data, falters under scrutiny. Astronomers turn inward, seeking analogs in our system. Seligman's team scans near-Earth asteroids, finding 6 with subtle non-gravitational shifts. These objects, small and rocky, lack cometary tails but move as if pushed. 1998, KY26, a 30-meter speck, spins every 10 minutes. JAXA's Hayabusa 2, fresh from Ryugu, targets it for a 2030 flyby. If it vents hidden gas, it could confirm the dark comet theory, linking Oumuamua to local cousins. The mission, a chance to touch the puzzle, carries humanity's hope for answers. These dark comets, if real, suggest Oumuamua wasn't unique. The solar system, once a closed bubble, emerges as a crossroads. Jupiter's gravity snares passing objects, some lingering in odd orbits. Asteroid 514107, Kaipioa-Wila, locked in resonance with Jupiter, may be interstellar, its chemistry alien. Comets like Hale-Bopp, rich in carbon monoxide, hint at distant origins. Each discovery, catalogued by observatories like Arecibo, reveals a galaxy where wanderers are common. The galaxy's highways hum with travelers, and Oumuamua was not alone. In August 2019, Gennady Borisov, an amateur astronomer in Crimea, spots another intruder named 2I Borisov. It blazes through the solar system, a comet with a glowing coma and a tail stretching tens of thousands of kilometers. Unlike Oumuamua's silence, Borisov announces itself, venting gas and dust as it nears the sun. Its carbon monoxide, abundant beyond local comets, points to a birthplace in a colder stellar nursery, perhaps 100 light-years away. Its hyperbolic path, like Oumuamua's, confirms an interstellar origin, entering from Hercules and exiting toward Telescopium. Telescopes, including the Swift Observatory, track its outgassing, a textbook comet born under another star. Yet its contrast with Oumuamua sharpens the mystery. One visitor, loud and bright, fits known physics. The other, sleek and silent, defies it. Together, they suggest a galaxy teeming with diverse wanderers, some visible, others elusive. Estimates from the University of Hawaii suggest thousands of interstellar objects cross Neptune's orbit daily, most too small or faint to see. The solar system, a speck in the Milky Way's spiral, lies on a busy route. Massive planets like Jupiter act as nets, temporarily capturing passers-by. Objects like Comet Makemake, with alien chemistries, may be relics of such encounters. These findings, published in Nature, reshape our view, casting the sun's domain as a galactic interchange. Oumuamua's acceleration, still unexplained, drives the search for answers. Bergner's dark comet theory gains traction, as lab experiments mimic its behavior. Water ice, irradiated for eons, releases hydrogen in controlled bursts, matching Oumuamua's push, but its shape 10-to-1 elongation challenges this model. Simulations at MIT suggest a natural body stretched by tidal forces near a star, yet no known process yields such extremes. Loeb's sail, a constructed artifact, remains a shadow hypothesis, unprovable without more data. The object's origin, traced by supercomputers at Oxford, remains elusive. Its path, rewound through the galaxy's gravitational maze, points nowhere precise. Stars in Lyra, like Vega, drift too fast to align with Oumuamua's past. Clusters like the Pleiades, 50 light-years distant, offer possible birthplaces, but simulations yield no matches. The object, drifting for hundreds of millions of years, erases its tracks, its surface a palimpsest of cosmic weathering. Its journey, solitary and vast, began before humanity's first fires. Project Lyra, launched by researchers in London, dreams of pursuit, a spacecraft, using Jupiter's gravity and a solar slingshot, could reach 70 kilometers per second, catching Oumuamua by 2048, launching between 2030 and 2033. It would brave the sun's heat, navigating a needle's eye in deep space. Yet the object, now a faint speck, poses a challenge. Its tumble, unpredictable after decades, complicates targeting. The mission, costing billions, bets on a single chance to touch the unknown. Closer to home, the Vera Rubin Observatory in Chile prepares for the next visitor, set to scan the sky in 2025. Its legacy, survey of space and time, will map every flicker, catching dozens of interstellar objects yearly. Unlike Oumuamua, spotted weeks after its closest approach, future travelers may be seen months ahead, allowing probes to intercept them. The European Space Agency's Comet Interceptor, launching in 2029, waits in space, ready to chase an incoming comet or alien object, its instruments primed for close study. These missions, born from Oumuamua's wake, mark a shift. Humanity, once reactive, builds tools to anticipate. The Rubin's 10-year survey, imaging the sky every 3 nights, will catalog larger, slower visitors, their paths traceable. Interceptor's flexibility, orbiting a stable point, lets it pivot to new targets. Together, they promise a harvest of data, revealing how often the galaxy sends messengers and what they carry: ice, rock, or something stranger. Its acceleration, if driven by radiation pressure, inspires new sail designs at institutes like Caltech. If a dark comet, it redefines cometary physics, prompting studies of local asteroids. The 1998 KY-26 flyby, planned by JAXA, tests this theory. Its data a bridge to Oumuamua's nature. If alien, it challenges our search for life, pushing projects like SETI to scan for physical artifacts, not just signals. The galaxy, a spiral of 200 billion stars, hides countless such objects. Oumuamua's path, crossing ours by chance, suggests others wait unseen. The local bubble, a 1,000 light-year cavity around the sun, formed by ancient supernovae, may channel these travelers. Its hot gas a highway for debris. Ambrosita's X-ray maps, from orbits beyond Earth's atmosphere, hint at tunnels linking such bubbles. A galactic network where Oumuamua once roamed. Oumuamua's trail, now cold, stretches toward Pegasus, a speck lost in the void. Its brief passage, a mere month in our skies, rewrites our cosmic map. Borisov's arrival, 2 years later, confirms the galaxy's restlessness. Its coma, glowing with carbon monoxide, spans 50,000 kilometers. A beacon from a star system colder than ours, tracked by the Chandra X-ray Observatory. Its outgassing mirrors local comets, yet its chemistry rich in alien ices sets it apart. These 2 visitors, one cryptic, one open, hint at a spectrum of interstellar wanderers. The dark comet theory, tested by local asteroids, gains ground. 1998 KY-26, a 30-meter rock, spins furiously, its orbit nudged by unseen forces. Hayabusa 2's flyby, planned for 2030, will probe its surface, seeking hydrogen trapped in irradiated ice. If confirmed, dark comets could number thousands in our system, their subtle pushes reshaping orbital models. The Pan-STARRS survey, which found Oumuamua, now hunts these ghosts, its data-feeding algorithms at the University of Arizona. Loeb's alien hypothesis, though divisive, spurs innovation. The Galileo project, funded privately, deploys telescopes to scan for artificial objects, probes, sails, or debris. Its arrays, dotting observatories in New Mexico, seek infrared signatures of technology, a shift from SETI's radio focus. Loeb's book, Extraterrestrial, argues Oumuamua's anomalies shape, shine, acceleration fit a crafted relic, perhaps a derelict probe from a civilization long gone. Critics, citing natural ices, demand proof, but the debate fuels curiosity. Oumuamua's acceleration, a tenth of a millimeter per second squared, remains the pivot. Models at the Max Planck Institute test exotic ice's methane, carbon monoxide sublimating, invisibly. None fully match the data. Solar radiation pressure, requiring a thin, reflective body, aligns better, yet Oumuamua's density, inferred from its tumble, suggests a solid core. The tension between theories drives experiments, from ice irradiation at CERN to sail prototypes at JPL. Each test, grounded in Oumuamua's clues, pushes science forward. The object's shape, a 10-to-1 ratio, haunts researchers. Tidal forces, stretching a body near a star, could form such needles, but require extreme conditions. Simulations at Stanford model a planet shredded by a white dwarf, launching elongated shards. Oumuamua, if such a fragment, carries a story of stellar violence. Alternatively, a flat disk, spinning like a coin, fits a sail's profile, its tumble a scar of ancient impacts. Without images, both shapes live in equations, a duality unresolved. The Rubin Observatory, its 8-meter mirror scanning Chile's skies, will spot them monthly, its deep exposures catching faint glints. Comet Interceptor, parked at a Lagrange point, awaits a slow-moving target, its spectrometers ready to parse alien ices. These tools, inspired by Oumuamua's escape, aim to catch travelers early, orbiting them for months. Such missions, planned by ESA and NASA, could sample surfaces, revealing compositions forged under distant suns. Its solar Obi-Earth maneuver, firing engines near the sun, demands precision. A probe, shielded against solar heat, would race past Oumuamua, imaging its surface at 20 kilometers per second. The data, beamed back by 2050, could show craters, fractures, or artificial seams. The mission's risk, a decades-long gamble, reflects humanity's drive to grasp the fleeting, a quest born in Oumuamua's wake. Formed 10 million years ago by supernovae, it spans 1,000 light-years, its edges birthing stars. Oumuamua, passing through, may have ridden its currents, guided by plasma tunnels mapped by Rosetta. These channels, linking bubbles across the galaxy, suggest a cosmic web where objects drift. Borisov, too, navigated this network, its path a thread in the Milky Way's tapestry. Humanity's watch extends beyond Oumuamua. Ancient Polynesians, navigating by stars, saw the same sky, unaware of its travelers. Today, amateurs with 10-inch scopes contribute to surveys, their data vital. The American Association of Variable Star Observers, logging Oumuamua's brightness, feeds global models. This blend of citizen and professional science, amplified by AI, scans for the next visitor, a collective effort to meet the galaxy's messengers. The galaxy itself, 200 billion stars strong, pulses with motion. Oumuamua's path, a chance crossing, mirrors countless others. Kaiapawawela, orbiting backward with Jupiter, may be a captured wanderer, its orbit a fossil of interstellar exchange. Comets like Hyakutake, their ice is alien, reinforce this flow. Each object, studied by telescopes like ALMA, reveals a solar system porous to the stars, a stage for cosmic encounters. Oumuamua drifts toward Pegasus, a silent speck in the galaxy's depths. Its passage, brief and baffling, leaves a trail of light and questions. Borisov, its cometary cousin, blazed through 2 years later, a reminder of the galaxy's restless traffic. Together, they reveal a solar system not isolated, but woven into the Milky Way's fabric, a crossroads where alien objects pass daily. The Rubin Observatory and Comet Interceptor, poised for action, stand ready to greet the next, their lenses and probes a bridge to the unknown. The object's acceleration, a faint push against the sun's pull, anchors the mystery. Bergner's dark comet, water ice venting invisible hydrogen, offers a natural path, grounded in lab tests. Loeb's light sail, a whisper of alien craft, challenges orthodoxy, urging science to stretch. Between them lie theories of exotic ice's nitrogen, Methane each tested, each flawed. Oumuamua's shape, elongated or flat, and its reflective surface defy easy answers. A riddle etched in starlight. The 1998 KY-26 flyby, probing local dark comets, may clarify its nature, linking the alien to the familiar. Project Lyra's dream, chasing Oumuamua to 2048, embodies humanity's resolve. Its solar slingshot, a fiery gamble, aims to capture images of a tumbling relic, be it rock or relic. The mission, though distant, echoes the Vera Rubin's vigilance, scanning for new travelers. These efforts, born from a single visitor, reshape astronomy, turning our gaze from static stars to dynamic intruders. The local bubble, its tunnels guiding such objects, frames this quest, a galactic stage where Oumuamua played its part. The galaxy's scale, 200 billion stars across 100,000 light-years, dwarfs our system. Oumuamua, ejected from an unknown star, drifted for eons, its origin lost in stellar orbits. Vega, once a candidate, drifts too far. Clusters like the Hyades offer no firm link. Yet its journey, scarred by cosmic rays, speaks of a universe in motion, where planets shatter and stars collide. Borisov, Kayapawawela, and others trace similar paths. Their chemistry's a record of distant worlds. Humanity's response, from Hawaiian telescopes to global observatories, shows a species awake to the cosmos. Ancient Sumerians, charting stars 5,000 years ago, saw the same sky, their clay tablets marking time. Today, we parse light with silicon, our data a modern epic. Amateurs, logging Oumuamua's flickers, join professionals at Keck and Hubble, a shared pursuit. This unity, sparked by a fleeting visitor, drives missions like Interceptor, ready to touch the next messenger. Its anomalies' speed, shape, acceleration force science to question assumptions. Dark comets, if real, redefine our system's boundaries. A sail, if true, redefines life's reach. Each theory, from Seligman's ice to Loeb's craft, pushes boundaries, sparking experiments and debates. The Galileo Project, scanning for artifacts, and Rubin's Sky Survey, hunting wanderers, carry this forward, a search for truths beyond our templates. The solar system, once a closed orbit, emerges as a galactic hub. Comets from the Oort cloud, nudged by passing stars, link us to the Milky Way's churn. The local bubble, carved by ancient explosions, channels these flows, its plasma tunnels a cosmic road. Oumuamua, Borisov, and future visitors ride these currents, their paths a story of creation and chaos. Humanity, watching from a blue speck, meets them with wonder, our tools and dreams aimed at the stars.
The universe balances itself upon a blade so fine that even the smallest tremor can send reality plunging into chaos. Everywhere we look in the cosmos, this delicate dance between structure and collapse plays out in breathtaking fashion. When magnetic energy surges within a star, it lashes outward as a solar flare that rips through the cold vacuum of space. When a supergiant begins fusing iron, it sets off a chain reaction so violent that the star unravels into a cataclysmic hypernova. And when pressure mounts within the crust of a spinning magnetar, the sudden crack of a starquake releases torrents of gamma radiation into the void. These moments are not merely dramatic events. They are cosmic tipping points, instances where matter and energy, pressure and temperature, order and entropy reach their critical thresholds. The entire universe, from the tiniest atoms to the sprawling clusters of galaxies, exists in a state of suspended equilibrium, and even the smallest disruption can ripple outward into profound transformations. And yet, miraculously, stability often reasserts itself. Subatomic safety nets emerge, hidden forces rally, and matter finds new forms to cling to. Like a cosmic version of Jekyll restraining Hyde, the universe somehow keeps its most destructive impulses in check at least most of the time. Nowhere is this tightrope more evident than in neutron stars. These are not just the remnants of stellar collapse, they are physics pushed to its breaking point. Imagine a star the size of a city, yet heavier than our sun, spinning dozens or even hundreds of times every second. Its gravity is so intense that if you were to drop something from shoulder height, it would reach half the speed of light before hitting the surface. Mountains here rise only fractions of a millimeter before the crushing gravity flattens them again, and the deeper one ventures into this stellar corpse, the stranger things become. The layers grow denser, the forces fiercer, and the laws of physics more tenuous. Understanding what happens inside neutron stars is not just an astrophysical curiosity, it is a gateway to understanding matter, space, time, and the very fabric of existence itself. Neutron stars are the last stronghold before matter folds in on itself completely. They are nature's ultimate experiment in extremity, a place where the universe tests its own limits, balancing on the razor's edge between endurance and collapse. To truly grasp these bizarre objects, we must start with the one star we know best, our Sun. On the night of December 24th, 2024, as families on Earth immerse themselves in the warmth of celebration, a spacecraft named the Parker Solar Probe was dancing through peril, traveling at 200 kilometers per second. It came within 6 million kilometers of the solar surface, closer than any human-made object has ever dared. That distance might seem vast, but in astronomical terms, it is as if the Parker Solar Probe had dipped a fingertip into the flames of a bonfire. It entered the corona, the Sun's outermost layer, a ghostly halo of superheated plasma that launches violent coronal mass ejections into space. These ejections are the Sun's tempests, storms of ionized matter so powerful they can knock out satellites and power grids on Earth. Yet the corona is not the whole story. Below it lies the chromosphere, a thin layer of fiery gases at 5,000 degrees Celsius. Beneath that lies the photosphere, the layer we see from Earth, a boiling ocean of plasma where hot gases rise, cool, and sink again in a mesmerizing dance. But to unlock the mystery of why the Sun burns and what it tells us about neutron stars, we must travel further back, not through space, but through time to colonial India in the early 20th century. Amid political upheaval and calls for independence, a teenager named Meghnad Saha found himself expelled from school for his role in protests against British rule. That same young man would go on to become a leading astrophysicist. In 1923, he developed the Saha ionization equation, a breakthrough that allowed scientists to calculate the degree to which various elements in a star are ionized based on local temperature and pressure. This was more than just a formula. It was a new way to read the Sun's inner workings. Ionization is the process by which electrons are stripped from atoms, turning ordinary gases into plasma, the fourth state of matter. Most of us learn in school about solids, liquids, and gases. Plasma is the realm beyond, an electrically charged soup of subatomic particles. The photosphere of the Sun is partially ionized, a mixture of gas and plasma. But as we dive deeper, the plasma becomes dominant. By the time we reach the core, we have entered a realm of unimaginable pressure. The temperature soars to 15 million degrees Celsius, and the density reaches 150 grams per cubic centimeter, 8 times denser than gold. In this inferno, hydrogen atoms are smashed together with such force that they fuse into helium, releasing immense amounts of energy. Every second, 620 million tons of hydrogen vanish, and 616 million tons of helium take their place. The missing mass is converted into energy, sustaining the sun's radiant glow. But this energy takes a long time to escape. On average, photons created in the core will take 170,000 years to fight their way to the surface. The balance between the outward pressure of this energy and the inward pull of gravity is what keeps the sun stable. This balance is known as hydrostatic equilibrium. Physicists describe this equilibrium using the equation of state, a formula that connects pressure, temperature, and density. In the sun, this equation is well understood, but things become more complicated as stars evolve. As they run out of fuel, the balance begins to falter. Gravity pushes inward with no opposition, and the star contracts. What happens next depends on the star's mass. Smaller stars become white dwarfs, stabilized by electron degeneracy pressure, a quantum force arising from the Pauli exclusion principle, which states that no two electrons can occupy the same state. The electrons resist being squeezed too close together, generating a pressure that halts the collapse. This was the insight of Ralph Fowler, whose wartime injuries led him to pivot from ballistics to astrophysics. Fowler's work laid the foundation for understanding white dwarfs and later, neutron stars. One of the most iconic white dwarfs is Sirius B, the pup. A companion to the bright star Sirius, though no larger than Earth, Sirius B is more massive than the Sun. Its matter is so tightly packed that a sugar cube of it would weigh as much as an elephant. Such density should cause collapse. Yet degeneracy pressure holds it at bay. But even this quantum pressure has limits. Subrahmanyan Chandrasekhar, building on Fowler's work, showed that if a white dwarf exceeds 1.4 solar masses, degeneracy pressure will fail and collapse will resume. This is the Chandrasekhar limit, the tipping point beyond which a white dwarf becomes a neutron star. In these more massive remnants, gravity crushes protons and electrons together to form neutrons. These, too, resist compression, thanks to neutron degeneracy pressure, offering one final buffer against total collapse. But what happens beyond this point, and what secrets lie buried in the heart of these neutron stars? That is the mystery we will begin to unravel in the chapters ahead. To study these cosmic balancing acts is to look into the fundamental nature of reality. Stars may burn and explode, collapse and flare, but always they reveal something about the rules that govern everything. And as we turn our gaze inward to the strange and powerful world of neutron stars, we begin to grasp the staggering question, how far can we push the universe before it breaks? The collapse beyond light. The tipping points that give birth to neutron stars are not isolated eruptions of energy, but part of a long and interconnected history of ideas, calculations, and revolutionary insights. Among the trenches of the First World War and the debris of fallen empires, a quiet intellectual revolution was stirring. When a French battleship disappeared beneath the waves in the Dardanelles in the spring of 1915, the headlines spoke of defeat. But in a hospital far from the front lines, a wounded soldier named Ralph Fowler began a transformation that would shift the course of theoretical astrophysics. His injury, suffered during the chaos of Gallipoli, led him to a new life among fellow scientists, where conversations and wartime improvisations laid the foundation for a new understanding of collapsed stars. The same bullet that pierced his shoulder ended a military career and opened the door to one of the most influential collaborations in modern science. Out of these connections, Fowler's curiosity began to pivot toward the stars. And by the 1920s, Fowler's work on quantum gases laid the groundwork for understanding the peculiar behavior of electrons squeezed into tight corners of space. This concept degeneracy pressure explained how white dwarfs resisted collapse. But it also planted a deeper question. What if gravity grew too strong, too relentless, even for this strange new pressure to resist? This puzzle was taken up by a young Indian astrophysicist named Subramanian Chandrasekhar. At just 19, aboard a ship sailing from India to Cambridge, he calculated the theoretical limit beyond which a white dwarf would be unable to resist gravitational collapse. This number 1.4 times the mass of the Sun became known as the Chandrasekhar limit. It was not just a mathematical threshold, it was a cosmic guillotine. Chandrasekhar's insight was met with skepticism. The idea that there existed a fatal weight limit for stars ran counter to prevailing beliefs. Among the most vocal critics was Arthur Eddington, one of the most prominent astronomers of the time, who believed the concept absurd. But physics does not yield to opinion, and eventually, the community recognized the significance of the limit. What followed next was an explosion in our understanding of stellar death. Stars above the limit could not become white dwarfs. Instead, they would collapse further, pushing beyond the realm of electrons and into a denser, more mysterious regime where protons and electrons combine to form neutrons. This new form of stellar remnant was compact beyond imagination. A white dwarf may be as dense as 1 billion kilograms per cubic meter, but a neutron star reaches densities 100 million times greater. A single teaspoon of neutron star matter weighs more than Mount Everest. This compression is so extreme that gravity reshapes the structure of matter itself, forcing it to become something altogether alien. The very existence of these stars challenges our most fundamental understanding of nature. To find one of the first physical clues of such bizarre objects, we look to the night sky. The Crab Nebula, a tangled mass of glowing gas and dust, marks the site of a supernova that lit up the skies in the year 1054. Ancient astronomers in China recorded the appearance of a new star, so bright it could be seen in daylight. But what they did not know is that deep within the center of this stellar shroud remained the collapsed heart of the exploded star. The core had been compacted into a neutron star, not just any neutron star, but one that spun rapidly, sending beams of radiation into space like a celestial lighthouse. Such spinning neutron stars came to be known as pulsars. They revealed themselves by their rhythmic flashes of light, first detected by radio telescopes in the 1960s. At the heart of the Crab Nebula, one such pulsar spins 30 times every second. And this is not even the fastest. Some rotate hundreds of times per second, their rotation preserved from the original spin of the massive star that gave birth to them. Like an ice skater pulling in their arms, the star's collapse accelerates the spin. But it is not only angular momentum that intensifies. The magnetic fields of neutron stars are also compressed and concentrated, reaching strengths that defy imagination. One neutron star's magnetic field can be 100 billion times stronger than that of a typical fridge magnet. In such extreme fields, physics becomes unpredictable. These stars are not simply objects. They are laboratories of fundamental forces. Yet even within their stability lies a question of limits. For just as white dwarfs had a maximum mass, so too must neutron stars. This realization led to the concept of the Tolman-Oppenheimer-Volkoff limit, a theoretical upper mass bound for neutron stars. If this limit is breached, not even neutron degeneracy pressure can withstand gravity's relentless pull. The star must collapse further. And the only known outcome of such a collapse is the formation of a black hole, a place where gravity overwhelms all resistance and not even light can escape. Neutron stars. Then, are the final checkpoint before the abyss. Yet their interiors remain a mystery. We cannot see inside them, and the pressures and densities involved are impossible to replicate on Earth. To understand them, astronomers must rely on indirect evidence timing the pulses of pulsars, measuring their masses, analyzing their cooling rates, and watching for minute variations in their signals. One particularly revealing discovery came from the Neutron Star Interior Composition Explorer, or NICER, a telescope mounted on the International Space Station. NICER's precision allowed astronomers to map the surface of a pulsar by observing the way its X-rays fluctuated. These maps hinted at mountains mere millimeters tall and gravitational fields that bent light so strongly. The far side of the star became visible. Such observations allowed astronomers to measure not only the size of neutron stars, but also to test different equations of state models that describe how matter behaves at such unthinkable pressures. But even among neutron stars, there are outliers. One in particular, known as J0740, puzzled scientists. Despite having more than twice the mass of the Sun, it was no smaller than other neutron stars of lesser mass. This contradicted expectations. In theory, more massive neutron stars should be more compact. Their gravity should squeeze them tighter. Yet J0740 defied this logic. Its size suggested either a misunderstanding of the equation of state or the presence of exotic matter within. Perhaps, deep in its core, the neutrons break down into their constituent quarks, or maybe even stranger particles, hyperons containing strange quarks, begin to emerge, creating a new state of matter. These questions highlight the frontier that neutron stars represent. They are not just remnants of stellar death. They are crucibles where the rules of physics are tested, stretched, and sometimes broken. To study them is to touch the edges of what is knowable. In these cosmic collisions and quiet pulses, we glimpse the universe in its most extreme form, and as we prepare to journey deeper into their interiors, we ask once more what hidden forces hold back the night. The architecture of collapse. Beneath the crust of a neutron star lies a territory so alien, so physically extreme, that every law of classical matter is rewritten. Just below its surface sits an atmosphere barely 10 centimeters thick, an envelope of hydrogen and helium glowing at temperatures near 2 million degrees Celsius. But this fragile veil is deceiving. What lies beneath is a fortress of incomprehensible pressure. Within moments of entering the crust, the atoms are stripped of their electrons, and the nuclei find themselves suspended in a sea of free-floating particles, packed so tightly that even light struggles to escape. It is here that electrons, neutrons, and protons begin to form patterns that defy earthly analogies, twisting and weaving into configurations born not of chemistry, but of nuclear geometry. This strange, dense frontier gives rise to one of the most exotic materials ever theorized, nuclear pasta. At such extreme densities, the forces between nucleons, protons, and neutrons begin to create structures as oddly familiar as they are entirely unprecedented, like culinary analogies forged in a quantum forge. These layers of matter contort into gnocchi, spaghetti, and lasagna-shaped formations. This isn't whimsy. These terms refer to real theoretical arrangements predicted by sophisticated computer simulations. Spherical clusters form bubbles resembling gnocchi. Flattened sheets echo the stretch of lasagna. Long filaments curve through space like strands of spaghetti. This pasta, however, is not dinner table fare. It may be the strongest material in the universe, 10 billion times stronger than steel. Though no laboratory on Earth can reproduce these pressures, Indirect evidence for the presence of nuclear pasta is mounting. The way neutron stars radiate heat, their spin-down rates, and sudden glitches in their rotation hint at structural rearrangements deep within. The rigidity of these pasta phases may even explain why neutron stars occasionally shudder in starquakes, a breaking of their internal architecture that releases bursts of radiation detectable across the cosmos. As we descend deeper, past the final folds of pasta, we encounter a domain where known matter begins to unravel. Neutrons, themselves once thought to be indivisible within stars, may begin to decay into their constituent parts. This realm remains hypothetical, but scientists believe that in the most massive neutron stars, pressure could become so great that even the neutrons lose their individual identities, dissolving into a fluid of quarks. Quarks are the fundamental particles that combine in threes to make up protons and neutrons. There are 6 known types: up, down, strange, charm, bottom, and top inside neutron stars. It is thought that only up and down quarks are typically present, but in extreme cores, strange quarks could emerge. This transformation yields what physicists refer to as quark matter, or more specifically, a quark-gluon plasma. In this state, the very building blocks of protons and neutrons slosh together in a sea of liberated particles, reminiscent of the conditions that existed in the first milliseconds after the Big Bang. These core regions would essentially host microcosmic echoes of the universe's earliest moment, a memory preserved in the heart of a dying star. But with this radical internal change comes an external paradox. If a neutron star becomes a quark star, an object made entirely of quark matter, then its density should increase further. This would, by gravitational logic, result in a smaller radius for more massive stars. Yet, observations like those of J0740 contradict this, implying that either quark matter behaves differently under pressure than expected, or that an entirely different form of matter exists at these depths. One such contender is dark matter, though still elusive. Dark matter is thought to comprise most of the universe's mass, exerting gravitational influence without emitting light. Some theorists propose that neutron stars, as they sweep through the galaxy, may scoop up dark matter, which then settles into their cores. If this dark matter interacts with itself or with baryonic matter, it could exert additional pressure or resist collapse in ways traditional models do not account for. This inclusion might help explain anomalously large neutron stars and open a new avenue for understanding both neutron stars and the universe's missing mass. Another theory gaining traction hinges not on exotic particles, but on quantum mechanics itself. Subatomic particles are defined not only by their mass and charge, but also by a quantum property called spin. Fermions, like protons and neutrons, have half-integer spin. And obey the Pauli exclusion principle, no 2 identical fermions can occupy the same quantum state simultaneously. This rule underpins degeneracy pressure. But bosons, particles with whole number spin, can share quantum states freely. If, under extreme conditions, fermions pair up to behave as composite bosons, they can collapse into a Bose-Einstein condensate, a state of matter where all particles move in concert as a single quantum entity. This possibility, though speculative, has profound implications. If the core of a neutron star transitions into a Bose-Einstein condensate, it may explain how these stars resist collapse even when exceeding conventional mass limits. It also reintroduces the name of Satyendra Nath Bose, the Indian physicist whose collaboration with Albert Einstein led to this prediction a century ago. In this way, the theoretical scaffolding of neutron stars ties back not only to astronomical observation, but to the deepest philosophical insights of quantum theory. Yet these stars remain mysterious partly because we cannot peel them open. We must rely on their emissions, on indirect measurements, and on the precise timing of the radiation they pulse into space. When two neutron stars collide, as happened in the event named GW 170817, we catch a rare glimpse into their interiors. The gravitational waves released carry information about their composition, while the light that follows from X-rays to gamma rays to visible light tells us about the debris. It is from these collisions that heavy elements like gold and platinum are forged. In a single explosion, the universe disperses its rarest treasures. All of this underscores a simple truth. Neutron stars are not merely remnants. They are living records of cosmic history, laboratories of extremes, and perhaps keys to unlocking fundamental truths about matter, gravity, and the evolution of the universe. They show us that at the edge of collapse, the universe invents new rules to hold itself together. The final barrier before the abyss. There is a boundary in the cosmos beyond which no force can resist collapse. If neutron stars are the last bastions against gravitational annihilation, then what happens when even they are pushed too far to understand this final tipping point? We must turn our gaze toward the darkest heart of astrophysics, where neutron stars can no longer hold their shape and instead fall into the abyss of black holes. But to reach that threshold, we must first examine how neutron stars walk their own perilous edge. The concept of a maximum mass for neutron stars, the Tolman-Oppenheimer-Volkoff limit, emerged in the early 20th century from minds struggling to quantify this final cosmic checkpoint. Early calculations placed this limit below the mass of the Sun, but modern refinements have pushed it closer to 2.2 solar masses, perhaps even higher. Anything beyond this and the neutron degeneracy pressure collapses like a scaffold torn from its foundation. The star succumbs to gravity in full, vanishing behind an event horizon from which no light can return. This transformation is not merely a continuation of stellar death, it is a redefinition of existence, where mass bends space-time so severely that even time itself seems to halt. But before crossing that threshold, neutron stars show signs of resistance. Some rotate at incredible speeds, and this spin helps counteract gravity. These millisecond pulsars, as they are called, generate centrifugal force that effectively adds structural support. The fastest spin measured so far exceeds 700 rotations per second. Like a figure skater spinning faster as they draw their arms inward. These pulsars use angular momentum to delay collapse, but even spin has its limits. When accretion from a binary companion increases the mass of a neutron star too far, not even rapid rotation can forestall doom. The best evidence for the final mass limit came not from theory, but from observation. In 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal labeled GW 170817. It came from the merger of two neutron stars, each roughly 1.4 times the mass of the Sun. When they collided, they did not immediately form a black hole. Instead, they produced a transient hypermassive neutron star that survived for mere moments before collapsing. The gravitational waves and the accompanying light burst allowed astronomers to narrow down the Tolman-Oppenheimer-Volkoff limit with greater precision. They now believe it lies between 2.1 and 2.3 solar masses. What happens when this limit is breached is astonishing. The neutron star, already more massive than the Sun and compressed into a sphere the size of a city, implodes. In a fraction of a second, it becomes a black hole. Its core contracts infinitely, forming a singularity, an object of infinite density and zero volume. Around this singularity, space itself is so warped that not even light can escape. The surface of no return is called the event horizon. Inside it, all paths lead inward. No message, no matter, no memory can pass outward again. And yet, this is where theory begins to fracture. General relativity, the framework that describes gravity, predicts this collapse with ruthless certainty, but quantum mechanics, the law book of the small, cannot accept infinities. According to quantum theory, singularities are mathematical monsters, signs that something in our understanding has gone wrong. This tension between the largest and smallest theories in physics fuels the search for quantum gravity, a unified theory that can describe what happens inside black holes. Neutron stars, teetering just above this brink, offer our best hope of finding that theory. Because their interiors reach conditions nearly as extreme as black holes just shy of total collapse, they represent nature's laboratory for testing new physics. If we can understand what matter does at these pressures, we might be able to avoid the infinities that plague singularities. Some theories propose that black holes are not singularities at all, but instead contain quark matter or even more exotic states. Others suggest that the cores of collapsing neutron stars might bounce, forming structures that mimic black holes but never fully become them. There are also quantum theories that challenge our assumptions about event horizons. Some posit that the intense information content of black holes results in firewalls, hypothetical regions of searing energy that would destroy anything falling in. Others suggest that quantum entanglement might allow information to leak back out, subtly encoded in Hawking radiation. But none of these ideas have been confirmed. They remain mathematical whispers, waiting for neutron stars and their death throes to speak the truth. The need for better understanding became urgent with the discovery of the most massive neutron star ever recorded, PSR J0952-0607. Weighing in at 2.35 solar masses, it appears to defy the supposed maximum limit. How can it exist? One answer may lie in its rapid spin, which could temporarily stave off collapse. Another possibility is that our equations of state the relationship between pressure, temperature, and density are still incomplete. If the matter inside neutron stars behaves differently than expected, perhaps they can support more mass. Some models now suggest that neutron stars might transform into entirely new classes of objects before collapsing into black holes. Among these hypothetical stars are quark stars, where matter exists not as neutrons, but as free-floating quarks. Others propose gravastars, where spacetime itself undergoes a phase change, creating a stable vacuum shell that halts collapse. These ideas are speculative but tantalizing, offering new ways to think about gravity and the limits of matter. Even more exotic are ideas linking neutron star interiors to dark energy, the mysterious force accelerating the expansion of the universe. If a form of dark energy exists inside neutron stars, it could produce repulsive pressure that helps resist collapse. This would not only explain unusually massive neutron stars, but also provide a direct connection between the tiniest and largest forces in the cosmos. And yet, all these questions return to a single point: what lies within. Neutron stars, by their very nature, hide their truths beneath layers of mystery. Their surfaces are calm, their pulses precise. But beneath that stillness lies the potential for transformation more violent and fundamental than any explosion. Their collapse is not just an ending, it is a threshold into the unknown. Stars that refuse to die. To follow the story of neutron stars to its end is to chase a paradox how something so small can contain such immensity, and how something so still can harbor such violent potential. As we look deeper into the strange physics of these compact remnants, we find that they are not the end of stellar life, but rather a crucible for new beginnings. Their collapse challenges our best theories, but their very existence offers something extraordinary, a window into the unification of the laws of the universe. Perhaps no mystery better captures this contradiction than the case of neutron stars that are colder than expected. In the summer of 2024, a team of astronomers led by Alessio Marino at the Institute of Space Sciences in Barcelona studied the X-ray emissions of 3 seemingly ordinary neutron stars. Using the Chandra and XMM Newton space telescopes, they expected to measure surface temperatures in the predictable range for their ages. Instead, they found something shocking. All 3 were between 10 and 100 times colder than their peers. This chilling result immediately challenged the assumptions encoded in most equations of state. The rate at which a neutron star cools is dictated by its interior composition. If particles within are able to shed energy efficiently, especially by emitting neutrinos, then cooling can happen far faster than standard models predict. Neutrinos, those ghost-like particles born in the sun and forged in nuclear reactions, are perfect emissaries for carrying away energy, but the degree to which they escape depends entirely on what lies at the star's core. If hyperons are present, or if matter has transformed into a superfluid or a Bose-Einstein condensate, the cooling will change drastically. In this way, each cold neutron star becomes a kind of thermometer, and what Marino's team found forced theorists to revise, eliminate, or reweight entire classes of internal models. This is the heart of the multi-messenger era of astronomy, observing the universe not just in light, but through gravitational waves, neutrinos, and other signals that cross traditional boundaries. Since GW 170817, more neutron star mergers have been anticipated and observed, though few so far have matched its clarity. Still, with each event, our models are tested anew. The hope is that one day, a merger will occur close enough, or aligned just right, to let us observe the entire process from the first ripple in space-time to the final burst of gamma rays. In such a moment, the veil may lift. Meanwhile, particle physicists continue their work underground, beneath kilometers of ice or stone, watching for signs of what lies within these cosmic anomalies. In the Antarctic, the IceCube Neutrino Observatory waits for a high-energy neutrino that might be born in a neutron star collision, or perhaps released in the collapse into a quark star. Other experiments attempt to simulate the pressures of neutron star cores using heavy ion collisions, briefly recreating conditions that existed moments after the Big Bang. And at the outermost limits of theory, physicists still dream of a deeper symmetry, one that combines general relativity and quantum mechanics into a single theory of everything. In this view, neutron stars are not curiosities but necessary guides. They compress mass and space into configurations that might act as test cases for string theory, loop quantum gravity, or other emerging frameworks. A neutron star may be as much a bridge to the quantum universe as the Large Hadron Collider. Their pulses, collisions, and cool silences may be datasets for the next generation of fundamental physics. There are even philosophers and cosmologists who see neutron stars as a kind of metaphor, the final act in a stellar drama, yet also a stage where the rules of the universe are rewritten. These stars are memory, fossil, and forge all at once, They remember their progenitor stars and preserve their angular momentum. They act as fossils, recording the gravitational behavior of matter under conditions unreproducible elsewhere. And they are forges, crafting the heavy elements that build planets, bones, and cities. In their silence, neutron stars speak volumes. The regular ticking of a pulsar's beam is the most precise clock in nature. Astronomers use pulsars to measure time better than atomic clocks, and to search for the slow rumble of gravitational waves from colliding galaxies. They are the metronomes of the cosmos, keeping time for an orchestra whose composition we have only just begun to decipher. And so the neutron star, once considered a dead end, becomes a new beginning. Its birth signals not just the death of a star, but the birth of insight. It connects thermodynamics to quantum mechanics, nuclear physics to cosmology, and the past of the universe to its future. In each of these collapsed stars is an unanswered question, a challenge to our hubris, a call to look deeper. One day, we may understand every layer of their interiors. One day, we may probe their cores with precision and map their magnetic fields in 3 dimensions. One day, we may even recreate neutron star conditions in the lab, or discover that their matter holds the key to dark energy or quantum gravity. Until then, we look to the skies and listen to their signals, aware that the most extreme objects in the universe may also be the most illuminating. Neutron stars remind us that the universe does not just explode, it compresses. It does not just create, it remembers. And it does not just end, it transforms. They are stars that refuse to die, and in their endurance, they may reveal to us what it means to exist at all.
At the center of our cosmic story, there burns a celestial titan silent, unblinking, and all-encompassing. It is the sun, the heart of the solar system, the luminous cradle of life. And yet, paradoxically, the harbinger of annihilation in the distant chapters of time. For as long as humans have cast their gaze skyward, this incandescent sphere has evoked awe, worship, fear, and inspiration. From the carved stones of Neolithic sites to the refined calculus of modern astrophysics, the sun has remained our oldest companion and most enduring enigma. It commands the dance of planets, breathes energy into the soil and sea, and shapes the rhythms of time. But it is not merely a backdrop to our existence. It is the very mechanism by which Earth breathes and survives. And though it rises each morning with gentle familiarity, the physics that drive this celestial engine are anything but ordinary. What appears to us as a golden disk is, in reality, a roiling ocean of plasma, a thermonuclear furnace of unimaginable intensity, a place where matter itself is stripped of identity and recast as pure energy. In this first chapter of our journey into solar truth, we peel back the layers of myth and light and descend into the intricate anatomy of the sun, a voyage from ancient reverence to atomic fire, from human meaning to cosmic mechanics. Though it sits 150 million kilometers away, the sun is our nearest star, and by far the most dominant object in the sky. Without it, our planet would be a frozen remnant drifting in darkness. With it, we are a vibrant oasis suspended in a vacuum. But this duality, the sun, as both giver and taker, has long haunted the human psyche. Early civilizations intuited its power in the cycles of growth and decay. To the Aboriginal Australians, It was a celestial being who traversed the sky each day, while to the people of ancient Mesopotamia, it was Shamash, the all-seeing eye of justice. The Inca worshipped Inti, and the Egyptians built entire temples aligned to the solar solstices, as if trying to etch human reverence into the architecture of time. Yet behind this cultural tapestry lies a deeper, more elemental reality. The sun is not a deity, but a star, a vast ball of gas and plasma, more than 1,000,000 times the volume of Earth, governed not by myth, but by the unyielding laws of physics. And at its core, hidden beneath thousands of kilometers of incandescent layers, lies the secret to all its power: nuclear fusion. The story begins in the solar core, a realm of immense pressure and temperature, where hydrogen atoms are forced into such proximity that they surrender their repulsive forces and merge. Through a sequence known as the proton-proton chain reaction, 4 protons are transfigured into a single helium nucleus, releasing energy in the form of photons and neutrinos. This is the birthplace of sunlight, though what we perceive as warmth and brilliance on Earth began its journey in darkness. At the heart of this crucible, the energy liberated here doesn't simply explode outward. Rather, it embarks on a slow, almost glacial trek through the dense radiative zone that surrounds the core. In this region, photons are scattered, absorbed, and re-emitted millions of times, progressing only centimeter by centimeter as they push against the tides of opacity. It can take between 100,000 and a few million years for a single photon to reach the next layer. It is a sobering thought that the light now warming your face may have been born before the first humans ever walked upright. Above the radiative zone lies the more dynamic and chaotic convection zone, a layer where energy transport shifts from radiation to motion. Here, the plasma is no longer so dense, and the trapped heat breaks free in buoyant loops, rising and falling in great convective currents. Hot material surges upward, releasing energy near the surface, before cooling and sinking back down to be reheated once more. It is in this ever-turning ocean of plasma that much of the sun's visible surface behavior is born: sunspots, granulation patterns, and the kinetic ballet of rising and sinking gas. The top boundary of this layer defines what we call the photosphere, the apparent surface of the sun, though it is not a solid one. Instead, it is the threshold where the plasma becomes transparent enough for light to escape into space, a luminous shell from which nearly all of the sun's visible light emanates. At roughly 5,800 Kelvin, the photosphere glows in a brilliant continuum of light, and it is this that we see when we look at the sun from Earth, filtered through our atmosphere into the golden warmth of day. Yet for all its brilliance, the photosphere is just a veneer, a fragile equilibrium maintained by opposing forces. The outward pressure from the fusion-powered heat within, counterbalanced by the inward tug of gravity, a standoff known as hydrostatic equilibrium. This balance is not permanent, but it is stable enough to hold the sun in its spherical shape and define the limits of what we perceive as its body. And just beyond this shell begins something far stranger and more formidable: the sun's atmosphere. Unlike the Earth, the sun's atmosphere does not gently thin into space. It flares upward in arcs, expands outward in gusts, and burns at temperatures 100 times greater than the surface below. The layers above the photosphere, the chromosphere, the transition region, and the corona are each more extreme than the last, culminating in a realm so hot and volatile that it defies our intuitive understanding of thermodynamics. This is where science begins to bend into mystery. It is here, in the enigmatic sheath of the solar atmosphere, that one of astrophysics' greatest puzzles resides. Why is the sun's outer atmosphere, the corona, vastly hotter than the layers beneath it? At the photosphere, the temperature is roughly 6,000 Kelvin, but ascend just a few thousand kilometers into the corona, and the temperature surges past 1,000,000. This counterintuitive phenomenon, known as the coronal heating problem, has stumped scientists for decades. It is akin to walking away from a fire and feeling warmer the farther you go. While several theories compete, ranging from magnetic wave heating to nanoflares and plasma turbulence, no definitive answer has yet been found. The corona is not just hot, it is alive with energy. Electrified tendrils of plasma are looped and twisted by magnetic field lines that erupt from the sun's interior like coiled serpents, arcing across tens of thousands of kilometers before collapsing back into the surface or snapping open into space. These magnetic loops are not mere visual phenomena. They are the engines of solar weather, the architects of violent solar flares and massive plasma ejections. They also help generate one of the most crucial and least visible forces in the solar system, the solar wind. As some particles accelerate past a boundary known as the Alfvén critical surface, they are no longer tethered to the sun by its magnetic field and are instead hurled into space at hundreds of kilometers per second. This constant stream of charged particles flows in all directions, creating an immense bubble around the solar system called the heliosphere, a shield of plasma and magnetic fields that envelops all the planets and forms the sun's long, trailing breath into interstellar space. The solar wind plays a vital role in everything from auroras on Earth to the behavior of comet tails to the shielding of planets from cosmic rays. And yet, its origins, how it is accelerated, shaped, and modulated, are deeply tied to the coronal processes that remain shrouded in mystery. To truly understand the sun, we must grasp this transition from the dense, energy-generating core to the ethereal, superheated fringes of its outermost layers. The sun is not a static object, but a layered, living system whose outer face is a shimmering interface between the known and the unknown. Each layer: core, radiative zone, convection zone, photosphere, and corona, operates on scales of temperature, time, and energy that dwarf anything experienced on Earth. And yet, it is from this incomprehensible furnace that life as we know it emerges. The sunlight that nourishes a plant leaf, the warmth that touches skin, the photons captured by a telescope's lens, all are born of nuclear collisions, billions of years in the making. They are shaped by the magnetic knots and plasma waves rippling across the solar surface, and they are ultimately released into the void, carrying with them a signature of the star from which they came. But even as we decode these patterns, the sun remains a creature of paradox. It is at once familiar and alien, constant yet dynamic, nurturing yet dangerous. Its light fills our days, but it hides 1,000,000 unseen forces. And as our instruments grow sharper, our models more precise, we are continually reminded that the sun's true power does not lie in its warmth alone, but in the unfathomable depths of its complexity. To study the sun is to confront a piece of the universe so overwhelming, so intimate, and so ancient that it reshapes the way we understand not just stars, but ourselves. And as we journey further into this blazing world, we find not only the physics of fusion and magnetism, but the fragile heartbeat of a planet that owes its every breath to a fire it can never touch. If the sun's surface were a shoreline of fire, then the corona would be the flame's impossible sky, an ocean of searing heat suspended not below, but above the hearth. It is the most paradoxical layer of the sun, at once distant and dominant, mysterious and ever-present, though barely visible to the naked eye, save for the rare moments of total solar eclipse when the moon briefly cloaks the photosphere in shadow. The corona is no mere afterglow, it is a tempestuous realm of arcing plasma, twisted magnetism, and inexplicable extremes. In the depths below, fusion burns steadily at 15 million degrees Celsius, yet the photosphere, the radiant surface we see, is far cooler, a gentle 6,000 Kelvin. But then somehow, impossibly, temperatures above this surface skyrocket by more than 2 orders of magnitude. Just a few thousand kilometers outward, in a sparse, whisper-thin plasma, the corona roars at millions of Kelvin, hotter than any furnace on Earth, hotter than most stars. This riddle, this inversion of thermal expectation, remains one of the most profound and enduring mysteries in all of solar physics, a phenomenon known as the coronal heating problem. How does the sun manage to heat its own atmosphere to temperatures so wildly disproportionate to its own surface? And what arcane forces lie at play in this ethereal inferno that breathes life, and sometimes chaos, into the solar wind? To grasp the true strangeness of the corona, one must abandon earthly intuition. Heat, in our experience, radiates outward and cools with distance. But in the sun, this is not so. Something stirs above the photosphere, accelerating particles and twisting fields, inflating the corona into a wild, lashing crown of magnetic loops and electrified tendrils. These luminous arcs, shaped by the complex and dynamic magnetic fields that rise from the convective flows beneath, are not mere ornaments, they are conduits of energy, highways for plasma, and possible keys to the mystery of coronal heating. Within these loops, conditions reach astonishing extremes. At their footpoints, magnetic energy accumulates and stores tension like a bowstring. When released, this energy can fling particles at breathtaking velocities and convert magnetic potential into heat with near-perfect efficiency. These localized magnetic explosions, whether they occur on grand scales, as solar flares, or on micro scales, as what researchers call nanoflares, could collectively inject the needed energy to heat the corona. But the mechanism remains elusive. And even after decades of solar observation, we are still only beginning to understand how such energy transfer might work in the turbulent ballet between magnetism and matter. The corona is not a static envelope, but a restless medium. Charged particles, mostly protons and electrons, swirl along magnetic field lines that twist and snap, surge and reconnect. Some of these particles rise and fall in arcs, looping back to the surface, while others reach an invisible frontier and are never seen again. This threshold, called the Alfvén critical surface, marks a profound boundary in the physics of the sun. Below it, plasma is tightly coupled to magnetic fields, corralled by invisible forces and pushed and pulled like puppets on strings. But beyond it, the balance shifts, the magnetic grip weakens, and particles gain the freedom to escape. Accelerated by mechanisms we still do not fully understand, possibly Alfvén waves, possibly reconnection jets, or some magnetic turbulence yet to be named, these liberated ions and electrons are cast into space as the solar wind. This wind is not like any wind on Earth. It is a supersonic stream of plasma that blows not across a landscape, but through the very fabric of the solar system itself, and it never ceases. The solar wind comes in two major flavors, a slow wind, meandering and dense, and a fast wind, swift and tenuous, originating primarily from coronal holes regions of open magnetic field lines on the sun's surface. Both contribute to the continuous outpouring of solar material, and together they form the vast and expanding bubble known as the heliosphere, an invisible sphere of solar influence that stretches well beyond the orbit of Pluto, shielding our planetary system from the full brunt of interstellar space. In this realm, the sun's influence reigns supreme. It is the boundary between the familiar and the unknown, between our star's breath and the cosmic winds of other stars. Within this bubble, the Earth swims like a small fish in a mighty current, bathed not only in warmth and light, but in radiation, magnetic storms, and charged particles shaped by the sun's mood, and that mood is far from constant. Like a heart that beats in magnetic rhythms, the sun undergoes an 11-year cycle of activity, a solar pulse that governs everything from sunspots to solar storms. At the beginning of this cycle, known as the solar minimum, the sun is relatively calm, its magnetic field ordered and serene. Few sunspots pepper its surface, and the corona is largely tranquil. But as the cycle progresses, differential rotation where the equator spins faster than the poles begins to twist the sun's magnetic field into knotted, tangled threads. Magnetic flux ropes rise and burst through the surface, creating sunspots dark, cooler regions where intense magnetic fields disrupt convection. These are not static blemishes, but dynamic cauldrons of activity, often serving as the birthplaces of solar eruptions. As these active regions proliferate, the sun enters the solar maximum, a phase of intense activity marked by a flurry of energetic events. Among the most dramatic of these are solar flares, sudden releases of magnetic energy that can hurl X-rays and ultraviolet light across space in mere minutes. These flares are often followed by even more consequential events, coronal mass ejections, or CNMEs. In a CNME, billions of tons of plasma are launched into space at speeds of up to 3,000 kilometers per second. If aimed at Earth, these ejections can buffet our magnetosphere, triggering geomagnetic storms, auroras, and in extreme cases, damage to satellites, power grids, and communication networks. The root cause of both flares and CMEs lies in a process known as magnetic reconnection, where opposing magnetic field lines snap and realign, releasing colossal amounts of energy in the process. It is this same mechanism, ironically, that may also play a role in heating the corona, a feedback loop of violence and renewal, of structure giving way to energy. But the importance of understanding the corona and solar wind is not just academic. In a world increasingly reliant on satellite technology, radio communication, and GPS systems, space weather, the environmental conditions in the near-Earth space, driven by solar activity, is no longer a curiosity, but a field of urgent, practical relevance. Solar storms can distort radio signals, interfere with navigation systems, and even pose radiation risks to astronauts in high-altitude flights. The ripple effects of a major CME today would be felt in everything from air traffic control to the synchronization of banking systems to the flow of electricity in our homes. Already, minor solar events regularly trigger alerts among space weather agencies. The threat is real and growing as we expand our technological reach farther into the heavens. Still, the grandeur of the corona transcends its hazards. In many ways, it is the sun's soul made visible, a place where plasma becomes sculpture, where light and magnetism twist into form. The corona breathes and pulses, ebbs and flows, whispering the deep time rhythms of a star that has been burning for over 4 billion years. Its mysteries are not just scientific. They are existential. What happens here, in this brilliant exosphere, tells the story of how stars live and die, how solar systems are shaped, how planets are born, and perhaps how they are ended. It is in this upper atmosphere that the seeds of space weather are sown. The solar wind is born, and the heartbeat of our star becomes most raw and exposed. The corona is not just an extension of the sun, it is a mirror into its inner life. And it is into this fire that we now dare to send our machines, instruments like NASA's Parker Solar Probe, the Solar Orbiter, and ground-based telescopes such as the Daniel K. Inouye Solar Telescope are beginning to offer new insights, closer and clearer than ever before. They map the sun's surface with millisecond precision, peer through filters into the ultraviolet and X-ray domains, and follow particles from their birth in the corona to their escape into the solar wind. They record the rhythms of solar flares, the fingerprints of wave-particle interactions, and the signatures of reconnection. Piece by piece, we are beginning to solve the puzzle to understand why the corona is so hot, how the wind is so fast, and what deeper processes guide the magnetic pulse of our star. But this knowledge comes with a melancholy kind of beauty, for in unraveling the secrets of the corona, we are also glimpsing the future of our sun. One day, billions of years from now, the hydrogen in its core will be exhausted, fusion will falter, the outer layers will swell and shed into space, and the sun's corona, once blazing at millions of degrees, will be cast off into the interstellar night. The heliosphere will collapse, the solar wind will cease, and what was once the fire at the heart of the solar system will shrink into a white dwarf, a cinder glowing faintly beneath the dust of time. Until then, we remain sheltered within its breath, warmed by its fire, and driven by our need to understand the furnace that made us. It begins not with thunder, but with light, an invisible flash in space, a tangle of magnetism snapping like a whip, a billion-ton scream of plasma hurled across the solar system. From the vast corona of our star erupts a coronal mass ejection, a storm born in silence, but destined to make noise across the cosmos. It races outward faster than sound, faster than comprehension, bound on a path that, with no ill intent and no malice, intersects the fragile bubble of human civilization. These are the moments when the sun reminds us not only of its grandeur, but of its reach, when the same force that nurtures the earth in golden light turns violent and surges against our world with a storm of fire and magnetism. These are the solar tempests unseen in daylight, felt in machines, and they carry with them the weight of cosmic power translated into earthly consequence. In this part of our journey, we step out of the solar atmosphere and into the domain of Earth's vulnerability, tracing the line from flare to fallout, from corona to catastrophe, and asking a question whose answer has never been more urgent. What happens when the sun strikes? Space weather begins far from Earth, but ends in its veins in the satellite constellations, power grids, aviation networks, and wireless systems that bind the modern world. Solar flares and coronal mass ejections are the primary actors in this drama. A solar flare is a sudden or intense burst of radiation resulting from magnetic reconnection in the sun's atmosphere. These flares emit vast quantities of electromagnetic energy, especially in the X-ray and ultraviolet bands, and they travel at the speed of light. Within minutes, they can reach Earth, disturbing the upper atmosphere and ionosphere, where they cause immediate changes in the density and behavior of the air through which our communication signals pass. GPS signals can falter. High-frequency radio waves can be absorbed or scattered, leading to degraded aviation communication, particularly on transpolar flights. But the flare is only the opening salvo. Often, it is followed by something more massive, more dangerous, and far slower, a CME, a huge cloud of magnetized plasma, launched like a solar tsunami into space, carrying billions of tons of charged particles and tangled magnetic fields. When a CME is Earth-directed, it takes anywhere from 15 hours to a few days to arrive. Depending on its speed, it crashes into Earth's magnetosphere, the invisible shield of magnetic field lines that surrounds and protects our planet from the solar wind. In normal times, this shield deflects the continuous stream of solar particles, but during a CME, the influx of energy can deform the magnetosphere, compressing it on the sunward side and stretching it into a long tail on the night side. As magnetic field lines are twisted and reconnected, they transfer enormous amounts of energy into the ionosphere, generating currents that ripple through the Earth's upper atmosphere. These are known as geomagnetic storms, and their consequences range from the dazzling to the destructive. On one hand, they trigger brilliant aurora as electrons collide with atmospheric atoms and molecules, exciting them to luminous release. On the other hand, they induce geomagnetically induced currents on the Earth's surface currents that enter power grids, pipelines, and undersea cables, stressing transformers and sometimes causing catastrophic failures. One such failure occurred on a frigid night in March 1989, when the Canadian province of Quebec was plunged into darkness by a geomagnetic storm. The sequence had begun a few days earlier with the emergence of a sunspot cluster the size of Jupiter. On March 9th, a CME erupted, and by the morning of March 13th, it had reached Earth. As the solar storm struck, electric currents surged through Quebec's power grid. In less than 90 seconds, the Hydro-Quebec system had collapsed, triggering a cascading failure that knocked out electricity for over 6 million people. Traffic lights died, heating systems stopped, radio stations fell silent, hospitals scrambled to engage backup power. Entire cities entered a sudden and eerie quiet. Engineers would later find that transformers had been saturated and relay systems overwhelmed by GICs generated in the bedrock beneath Quebec's grid. This storm, now known as the Quebec Blackout, became the first major infrastructure collapse definitively linked to solar activity. It was a harbinger of what space weather could do in the digital age, but not the worst we've ever seen. To glimpse that, we must turn the pages back to the 19th century, to an age of iron wires and ink, an era that bore witness to a solar event so colossal that its light and fire danced across the entire planet. On September 1st, 1859, British astronomer Richard Carrington was observing the sun when he saw something no one had ever seen before: a blinding flash of white light emerging from a sunspot group, lasting for less than a minute. This was the first ever recorded solar flare, and it marked the onset of what would become known as the Carrington event. Just hours later, a CME slammed into Earth so quickly that it is believed to have been preceded by a previous eruption that cleared a path through the interplanetary medium, allowing the second, faster CME to travel at unprecedented speed. The result was a geomagnetic storm of historic proportions. Auroras lit up the skies not only in high latitudes, but as far south as Cuba, Mexico, and even Hawaii. In cities, the skies turned red and green like shimmering celestial fire. In Colorado, gold miners reportedly woke in the night, thinking it was dawn. Telegraph systems across Europe and North America went haywire. Sparks flew from telegraph pylons. Some systems continued to transmit even after being disconnected from their power sources, driven entirely by the induced currents from the storm. Operators were shocked by their equipment. Messages were burned into paper. It was a moment when the sun reached through space and etched its presence into our machines. Though few lives were directly lost, the Carrington event exposed a truth that remains ever more relevant. Earth is not isolated from its star. The thin shell of magnetism and atmosphere that surrounds us is vulnerable to solar wrath. And today, our systems are far more complex, interconnected, and fragile than in 1859. If a similar storm were to strike now, the effects could be catastrophic. GPS constellations would be degraded or disabled. Aviation would face severe route disruption, particularly on polar routes. The internet, reliant on undersea cables and synchronized timing systems, could face interruptions. Power grids in vulnerable regions, especially those at high latitudes with long transmission lines, could fail, causing blackouts that last not for hours, but for days or weeks. Water treatment systems, emergency communications, banking transactions, and even stock exchanges could all be affected. The cost would not merely be technical, but deeply human, interrupting healthcare, endangering lives, destabilizing economies. Studies by NOAA and the National Academy of Sciences have estimated that a Carrington-class storm today could inflict damages ranging from $750 billion to over $3 trillion in the United States alone. Globally, the impacts could echo the disruption seen during the COVID-19 pandemic, but in some respects, with even less predictability and less resilience. It is not just the scale of disruption, but the stealth of its arrival that makes solar storms uniquely dangerous. Unlike hurricanes or earthquakes, which give some signal or warning, a CME can travel so quickly that humanity may have less than a day to prepare. The window for defense is short, and many regions lack hardened infrastructure or dedicated forecasting systems. Moreover, the effects may not be uniform. While some parts of Earth's magnetic field are better shielded, others, particularly in the northern latitudes and areas built on resistive rock, are far more exposed. A storm could simultaneously trigger brilliant auroras, in one part of the world and bring down an entire power grid in another. The interconnectedness of modern systems means that a failure in one region can ripple outward, magnified by the fragility of global infrastructure. And still, many are unaware of this celestial threat. It would be easy to dismiss these concerns as speculative until we consider that we already came within a cosmic breath of disaster. On July 23, 2012, during the peak of the last solar cycle, NASA's Stereo A spacecraft recorded a powerful CME. It originated from the far side of the Sun. The eruption was massive, fast, and perfectly structured to produce geomagnetic chaos. Had it occurred a week earlier, when that region of the Sun was facing Earth, it would have struck our planet head-on. Researchers analyzing the data later concluded that this CME was on par with the Carrington event, and that its passage through space had been facilitated by an earlier CME, just like in 1859. The Earth was spared by a matter of solar rotation, a difference of a few degrees and a few days. It was, in a sense, a bullet dodged in slow motion. The warning was not theoretical. It happened, and it may happen again. As we move further into the 21st century, the likelihood of such events and our exposure to them will only increase. Star Cycle 25 is now well underway, and many researchers expect its peak to arrive in the next year or two. Already, we are seeing an uptick in solar flares and active sunspot groups. The Parker Solar Probe, Solar Orbiter, and ground-based observatories like DKIST are now monitoring the sun's behavior in unprecedented detail, yet our preparedness remains uneven. Some nations have launched mitigation programs developing early warning satellites, reinforcing transformers, and issuing space weather forecasts. Others remain dangerously unaware. Space weather, like climate change, is a global issue that requires global cooperation. Because the sun plays no favorites, its storms do not recognize borders. And so we find ourselves suspended between knowledge and risk, between what we have come to understand about our star and what remains to be done to safeguard the fragile technologies that orbit and inhabit our world. The same force that once ignited awe in ancient stargazers now powers the fears of modern engineers. The auroras, for all their beauty, are not just spectacles, they are the glowing edges of danger. And while we marvel at them, we must also reckon with their origin, a sun that remains powerful, unpredictable, and intimately connected to our survival. There is a moment, just before dawn, when the sky begins to whisper secrets from the stars. The deep blue fades, the air shifts, and somewhere just beyond the veil of atmosphere, the sun prepares to rise again, an act so commonplace we seldom stop to think of it. And yet, for all the reverence and routine we place upon its daily emergence, the sun remains one of the most enigmatic objects in the universe. Its heat nourishes life, but its storms can destroy it. Its light reveals the world, but its own heart remains hidden behind blinding brilliance. For centuries, we looked up in awe, squinting through rudimentary telescopes or shielding our eyes behind smoked glass. We mapped sunspots, charted solar cycles, and wondered what caused the sun to pulse, flare, and breathe fire into the void. But in the last few decades, something changed. We stopped merely watching the sun, we began chasing it. We built machines that could stare directly into its fury, crafted instruments that could taste the solar wind, and eventually launched a probe daring enough to dive into the solar atmosphere itself. This is the story of our long journey to understand the star we call home, not just as an object of worship or wonder, but as a living, dynamic force of nature that shapes our world in ways both subtle and profound. It began with a simple desire to see more clearly. In the 1990s, the Solar and Heliospheric Observatory became our first great sentinel of the Sun, a joint mission by NASA and the European Space Agency that revolutionized our understanding of solar behavior. Launched in December 1995, SOHO was positioned at the Lagrange point, on a gravitationally stable region roughly 1.5 million kilometers from Earth, where it could keep constant watch over the Sun without being blinded by Earth's glow. From this privileged vantage point, SOHO peered into the inner mechanics of our star with instruments that could image in extreme ultraviolet, detect oscillations on the Sun's surface, and observe the faint corona in unprecedented detail. It was here, through the lens of SOHO, that we first witnessed the true drama of the Sun's outer atmosphere massive coronal loops, swirling prominences, and the explosive release of coronal mass ejections. It also paved the way for a new field of study called helioseismology, the science of interpreting sound waves rippling through the solar interior, allowing scientists to infer the Sun's inner structure in much the same way seismologists study the Earth's core. SOHO wasn't just a satellite. It was our first true sun watcher, and it revealed a star far more dynamic, volatile, and complex than we had ever imagined. But the Sun is not static, and neither could our observations be. The early 2000s brought with them a new era of solar monitoring with the launch of Stereo, a pair of spacecraft designed to give us stereoscopic vision of the Sun. Launched in 2006, Stereo A and Stereo B were placed in orbits that gradually separated, one moving ahead of Earth and the other falling behind. This innovative configuration allowed scientists to see the Sun in 3 dimensions for the first time, providing a fuller view of solar eruptions and how they evolve in space. It was Stereo A, in fact, that recorded the near-miss Carrington-class CME of 2012, a solar bullet that missed Earth by less than a week. Without Stereo, we might never have known just how close we came to global catastrophe. But beyond its warning shot, Stereo offered something more lasting. It gave us the ability to track solar storms from their birth on the solar disk to their arrival at Earth, offering better models, earlier warnings, and a more complete understanding of how the Sun's emissions interact with the solar system. Yet as powerful as SOHO and Stereo were, they were still watching from a distance. To truly understand the Sun, to answer the riddles of the corona and the solar wind, we needed to get closer. In 2010, NASA launched the Solar Dynamics Observatory, a next-generation platform equipped with an array of high-definition instruments capable of imaging the Sun in 13 different wavelengths of light, every 10 seconds, around the clock. SDO's cameras revealed the Sun as a shifting tapestry of magnetic fields and plasma currents. It traced the birth of sunspots, the twisting of magnetic ropes, and the slow unfurling of filaments and flares. With SDO, we didn't just see the Sun's surface, we saw its personality. And that personality was moody, ever-changing, and governed by forces that stretched deep into its core and far beyond its surface. SDO allowed us to connect surface activity with atmospheric reactions, helping to decode the solar cycle. refine models of flare prediction, and deepen our appreciation for the complexity of heliophysics. But still, even SDO, with all its sharp eyes and ultraviolet insight, could only observe from orbit. The next leap would require something more audacious, something unthinkable until only recently. Enter NASA's Parker Solar Probe, the crown jewel of solar exploration, and the most daring mission ever conceived to study the sun, named after the pioneering astrophysicist Dr. Eugene Parker, who in the 1950s first theorized the existence of the solar wind. This spacecraft is not simply observing the sun, it is flying into it. Launched on August 12, 2018, the Parker Solar Probe is the fastest human-made object in history, hurtling through space at speeds approaching 700,000 kilometers per hour and diving closer to the sun than any spacecraft ever before. Its mission is as poetic as it is scientific to touch the sun, not just metaphorically, but literally by entering the corona and sampling its plasma directly. Such a feat demands unprecedented engineering. Parker is protected by a carbon composite heat shield capable of withstanding temperatures over 1600 Kelvin, while its instruments operate in the cool shadow just behind it. This shield, barely 11 centimeters thick, is all that stands between the probe and a fiery death as it navigates the outer reaches of a star that can melt metal and ionize atoms in an instant. What Parker has already accomplished is extraordinary. Within its first few orbits, it made history by crossing the Alphen critical surface, becoming the first spacecraft to enter the solar corona. This boundary, where magnetic forces no longer dominate the motion of particles, marks the threshold between the sun's atmosphere and the solar wind. In doing so, Parker provided the first direct measurements of coronal conditions' density, temperature, particle velocity, and confirmed theories that had long lived only in models. It recorded magnetic reversals known as switchbacks, sudden S-shaped kinks in the magnetic field that flip direction and may hold the key to understanding how the solar wind is accelerated. These switchbacks were once thought to be rare, perhaps confined to the solar poles, but Parker found them in abundance, suggesting that the corona is far more dynamic and turbulent than previously believed. It also measured high-frequency plasma waves, turbulent flows, and even traced some switchbacks back to magnetic funnels rooted in the sun's surface regions between convection cells that may act as solar wind launch sites. In mapping these phenomena, Parker has begun to answer the deepest questions of solar physics. Why is the corona so hot? How does the solar wind escape? What triggers the magnetic reconnection events that power solar flares with each flyby? Parker draws a little closer, gathering data that will rewrite textbooks, improve space weather forecasting, and enrich our understanding of stellar processes throughout the universe. And it's not done yet. The mission is set to continue through late 2025 using gravity assists from Venus to spiral ever closer, until it flies within just 6.1 million kilometers of the photosphere, roughly 4% of the Earth-Sun distance. At its closest approach, Parker will be moving fast enough to travel from New York to Tokyo in under a minute, racing through plasma storms and recording every magnetic twist it encounters. But perhaps the most thrilling aspect of these encounters is also the most vulnerable during these close passes. Parker cannot transmit its data. It must endure the firestorm in silence, store its observations on board, and then beam them back once it escapes to safer orbit, like a messenger returning from a realm of gods with sacred truths clenched in hand. And these truths are not just about the sun. They ripple outward, informing our models of other stars, our understanding of space weather, and our hopes for protecting Earth's future. As we send more astronauts into space, build satellites in low and medium Earth orbit, and expand missions to Mars and beyond, knowing how our star behaves is not optional, it is essential. Parker is not alone in this pursuit. It works in tandem with missions like ESA's Solar Orbiter, which captures high-latitude images of the sun's poles, and the Daniel K. Inouye Solar Telescope, which captures the most detailed surface images of the sun ever recorded from Earth. Together, these instruments form a celestial symphony, each offering a different angle, a different note in the grand composition of heliophysics. From high-resolution imaging to plasma detection, from ultraviolet spectroscopy to magnetic field tracing, the human endeavor to understand the sun has never been more focused, more capable, or more necessary. And yet, even as we peel back the layers of our star, we are humbled by what remains. For all our spacecraft and algorithms, the sun is still a mystery. Its interior remains unseeable, its long-term behavior unpredictable. We do not yet fully understand how its magnetic field reverses every 11 years, or why one cycle is more intense than another. We cannot yet forecast flares with the precision we require, nor can we fully shield our infrastructure from its most violent moods. The sun, in many ways, is a wild and ancient thing, a being of plasma and magnetism that operates on scales of time and energy beyond human grasp. But by daring to approach, by reaching out with instruments forged in the minds of dreamers and engineers, we bring ourselves closer to the language of the universe. We touch the fire, not to be consumed, but to be transformed. As Parker completes its remaining orbits, it will continue to rewrite what we know. Its final dives into the corona will be the closest any human-made object has ever come to a star. And then, inevitably, it will drift beyond use, its fuel spent, its instruments silent. It may remain in orbit around the sun for centuries, perhaps millennia, before eventually succumbing to the same star it once studied, burning up in a final embrace. But the legacy it leaves behind, the data, the insight, the wonder will endure far longer. It will shape missions yet unborn, shield technologies yet unimagined, and perhaps one day save lives from a solar storm we cannot yet foresee. In that way, Parker is not just a spacecraft, it is a bridge between our world and our star, a testament to the human spirit's refusal to settle for shadows when the source of light itself can be pursued. There are missions we plan and missions we dream. Then, once in a generation, a mission emerges that belongs to both the culmination of decades of engineering and wonder, calculation and courage, charting a path not just toward data, but toward meaning. The Parker Solar Probe, humanity's bravest emissary to the sun, has already transformed how we understand our star. It has crossed boundaries once thought unreachable, tasted the breath of solar wind, and traced magnetic veins buried deep in the sun's beating heart. But now, in 2024, it approaches its most daring act, the final, closest flyby, a descent into brilliance and chaos that no machine before it has ever dared. It will draw within 6.1 million kilometers of the photosphere, a mere whisper from the sun's surface in cosmic terms, and it will do so at a velocity of 690,000 kilometers per hour, a speed so staggering it defies ordinary comprehension. It will be humanity's swiftest journey and its most fragile. For in those moments when Parker becomes a sun chaser at the edge of obliteration, the probe will carry with it not only instruments and software, but our collective need to understand where we come from and how we survive in the cradle of fire. This ultimate perihelion, scheduled for Christmas Eve, 2024, is no ordinary pass, unlike its previous dives, which already tested the limits of materials science and human foresight. This approach will take Parker twice as close as its 2021 coronal transits. The temperatures will exceed 1600 Kelvin, and the particle environment will be so dense and turbulent that even its hardened heat shield, the carbon composite armor honed over years of development, will strain under the pressure. But Parker is ready not just to survive, but to listen. During this final plunge, it will measure the microscopic structures of coronal plasma, sample the acceleration patterns of charged particles, and map the magnetic topology of switchbacks and reconnection sites with exquisite precision. The mission's overarching goals converge here to resolve the solar wind's mysterious acceleration, to decode the mechanisms of coronal heating, and to understand how energy is transferred from the sun's surface to the stream that stretches across the solar system. What once were textbook footnotes and mathematical theories will now be tested in the field of fire itself. But the most delicate part of this final encounter is not the heat or speed, it is the silence. Parker cannot communicate during its closest pass. When it enters the innermost corona, the intensity of radiation and plasma distortion will make real-time transmission impossible. It will fly blind to us, recording everything it sees, everything it feels, and storing it on board. Only once it retreats, coasting back to a safer distance, will it be able to offload its data, assuming it survives the trial. It is a moment of profound tension for several hours. The most advanced spacecraft ever built, moving faster than any object in human history, will be completely alone inside a star's atmosphere. No signal, no telemetry, just Parker, racing through plasma storms with its electronic ears wide open. And if it speaks again, it may do so with answers that reshape solar science for decades to come. Those answers will not come in grand revelations, but in patterns, pulses, and fields. Parker will trace the substructures of solar wind, identifying where and how it picks up speed, whether through wave-particle interactions, magnetic funneling, or some hybrid process not yet imagined. It will examine how switchbacks, those magnetic S-shaped reversals, arise in the boundary layer between the photosphere and corona, and whether they are rooted in convective cells, turbulent wave fronts, or reconnection sites near the surface. It will also probe the fine-scale variability in electron and ion densities, helping scientists understand how mass and energy propagate through stellar atmospheres, a discovery with implications not just for the sun, but for stars across the galaxy. Each bite of Parker's recorded experience will be pored over, modeled, and cross-checked with data from Solar Orbiter, SDO, and ground-based telescopes in a global effort to decode the language of the sun. Beyond 2024, the mission still has life in it. Parker is scheduled to make at least 2 more close approaches, reaching similar distances to its final 2024 perihelion. However, these will likely be less intense, as its orbit will gradually drift outward due to the lack of further Venus gravity assists. After its last scheduled flybys, the mission will enter a phase of diminishing returns, where orbital stability can no longer be maintained. At some point in the next few years, perhaps by the mid-2030s, Parker will exhaust its fuel not because it ran out of ambition, but because orbital correction and thermal orientation require propellant. Once its final maneuvering capabilities are gone, the probe will begin a slow and inevitable decay, spiraling inward on a terminal trajectory. Eventually, it will reach a point of no return, falling into the solar atmosphere not as an observer, but as an offering to be melted, vaporized, and absorbed into the very body it was sent to study. There is something deeply poetic in that ending, unlike Voyager, which will drift endlessly into interstellar night. Parker's fate is to burn in the light. It will return, atom by atom, to the star from which all our atoms were forged. It will end not with a signal, but with a silence deeper than data, a gesture of reverence to the furnace that birthed Earth and all life upon it. And yet, in that silence, it will leave behind a chorus of knowledge, thousands of terabytes of measurements, patterns, and revelations that will keep scientists busy long after its sensors are stilled. Its legacy will not be its death, but its descent. And what a legacy it is. Parker is already changing how we think about stars. It is revealing how magnetic chaos and plasma turbulence are not mere quirks, but fundamental aspects of stellar behavior. It is bridging the gap between solar physics and astrophysical plasma dynamics, showing us how similar mechanisms might shape the winds of red giants, the outbursts of pulsars, and the envelopes of young suns yet to ignite their fusion hearts. It is also redefining how we prepare for the future, both in terms of space weather forecasting and in the design of next-generation spacecraft that may one day orbit other stars. By knowing our sun in such intimate detail, we are building a model of stellar physics applicable across the cosmos. And perhaps more importantly, we are future-proofing our civilization. The more we know about solar storms and their triggers, the better we can shield our satellites, protect our astronauts, and stabilize our infrastructure. Because make no mistake, the stakes are high. We are now a technological species, vulnerable to the whims of a magnetic storm. GPS, internet backbones, aviation navigation, and even global finance all can be affected by the sun's temper. Parker's mission is, in part, a Sentinel project, a way to better anticipate the next Carrington-class event before it arrives. The 2012 near miss was a cosmic warning shot, and Parker is our best tool for heeding that warning. As it completes its arc, each flyby becomes more than science. It becomes insurance for the world we've built on circuits and signals. But beyond the science, beyond the policy and prediction, there lies something deeper. To touch a star is not just a feat of engineering, it is a message to the universe. It is a whisper that says we are not afraid. We will go where fire lives. We will not settle for safe distances or soft glows. We will descend into brilliance, even if it costs us everything. Parker's journey is not just NASA's, it is ours. It is the story of a species that emerged from stone and instinct and built a vessel with its bare hands and bold mind, aimed it at the most dangerous object in the sky, and said, "Go." There is something eternal in that act, For long after Parker is gone, long after its circuitry is dust and its orbit is ash, it will remain in our minds as a symbol of what science is and what it can be, not merely the accumulation of facts, but the expression of awe, not just analysis, but poetry. In the final accounting, Parker is not just a probe, it is a kind of sunlit elegy, an ode to the star that sustains us, and to the spark in us that dares to know it. And one day, when another storm rises, when solar flares crackle across the sky, and auroras dance in unlikely latitudes, we will look up not with fear, but with understanding. And we will remember the machine that went into the fire so that we could stand in the light. In that moment, the mission will be complete, and the sun, at last, will no longer be a mystery, but a mirror